So once again, the center of mass is the average position of a system of particles. And now we've looked at how we can calculate an average. So let's look at how we calculate the center of mass. So looking at our first example, we had a single particle of mass m. We had a second particle of mass m. And we said they were a distance d apart. So we'll set the position of the first particle to be x equals 0. And the second particle to be at x equals d. So if we look at the mass as the weight of these particles, we see that the center of mass is m times the position of, so the mass of the first particle times its position, plus the mass of the second particle times its position, divided by the total mass. In other words, the m's cancel out, and we just say that the center of mass is at d over 2. Well, that's good. That's exactly where we expected it to be. Now let's look at a similar case. Now we're going to have two masses that we stack on top of each other, and a third mass off to the side. So once again, we'll put the two particles at x is 0, the third particle at x is d. So now our center of mass is m, the mass of the first particle times 0, the mass of the second particle times its position, the mass of the third particle times its position, and divide by the total mass. So we see that we get a center of mass at d over 3. Meaning, if d over 2 is the halfway point between the particles, the center of mass is actually shifted toward the two masses. So it's exactly as we predicted that it should be before we looked at it mathematically. But mathematically we see that what we're really doing is our weights in our average are actually just the masses. And the way that we can see that is, what if we take these two masses and we just combine them to a single particle who's with a mass of 2m, and we look at the same system. So again, we have x is 0 and x is d. So now we see that the center of mass, if we write it as a weighted average, is 2m times 0 plus m times d all over 3m, because once again the sum is still 3m, so we still get d over 3. So in other words, we could take these two particles that were stacked on top of each other, and we can actually just make them into a single particle, and we'll get the same center of mass in both cases. So now we can develop a formula for center of mass. We can say that the center of mass is equal to 1 over the total mass of mass 1 times position 1, mass 2, position 2, and we do this for all n particles. But of course, notice this is a vector. The center of mass is a vector. In other words, if I can look at the x component and say the x center of mass is m1 times the x position of particle 1 plus m2 the x position of particle 2 plus mn the x position of particle n. And similarly, for the y center of mass, I can call, sorry, I'll change the color for you. So the y center of mass is m1 y1 m2 y2 mn yn. And then our answer is still going to be a vector. So for example, I can have one mass located at y equals at x equals 0 and y equals h, I can have another particle at x equals 0, y equals minus h, and then I can have a third particle at x equals d, y equals 0. So we see that, so we've already seen, if we look at the x center of mass, the x center of mass is just d over 3. Now to look at the y center of mass, we see that's m times h plus m times minus h plus m times 0, all divided by 3m. Well, that term goes away. These terms cancel. So the y center of mass is at 0, which means the center of mass of the system is going to be at d over 3, 0, or d over 3 x hat. In other words, we can treat the x and y components completely separately. We can solve and find what the x center of mass is, and then completely separately find the y center of mass because they're vectors. This is the first example where we're seeing something in physics that shows us how vectors can be really useful. Because imagine if we weren't using vectors and we just had to look at the positions of these. We could imagine, it can be very difficult as we get a large number of particles to figure out exactly what the center of mass is. Whereas in this case, because they're vectors, we can just look at all the x and y components separately, and then we'll get a total quantity. And also notice that this 3-particle system now has the same thing. If we had taken those 2 particles and put them together at the origin, it has the same exact center of mass. And so we're going to start to make more use of that once we start to look at realistic systems of particles and see what things are really made out of.